Today I'm sitting here with Eric Little, co-founder of Edison Motors, and we're going to ask him some more technical questions. So to begin with, Eric, why don't you start off telling us what is your role at Edison Motors?
Well, Theron, thanks for having me. So my name is Eric Little. I'm co-founder as well as technical officer at Edison Motors.
With the Edison trucks being a diesel-electric truck, people think of it more of as a hybrid system, but it's not quite. So can you tell us how the power flows with your trucks? It's not shared, it's...
Yeah, so it's a really cool approach to this design. So instead of just being a hybrid drivetrain, which has been done in the past, we actually kind of went to the drawing board, did something brand new. So we did is, it's called a range extended EV, or range extended electric vehicle. What it does is actually has a pure electric drivetrain. And what we do is we just so happen to have a diesel generator on board, which charges the batteries, not actually energizing or rotating any shafts for a driveline.
So the power is going from the generator to the batteries to the drive shaft.
Yeah, kind of. I mean, another way to look at it is actually...
Not drive shaft.
It's actually going from the batteries to the electric motors. It just so happens to have a generator on board, which charges the batteries, as well as obviously sends power through the batteries to the drive motor when you're going down the road and need that extra range.
And it doesn't actually, I said to the drive shaft, but it doesn't even have a drive shaft.
Exactly. Well, I mean, when we built Carl, we learned fast that we have to eliminate the drive shaft. And it's great to see, right? Tesla now has their electric vehicle out and they don't have a drive shaft. So we feel like we were almost ahead of the curve there.
How is it that you were able to eliminate the drive shaft? What is in replacement of?
It's clever engineering. So instead of having a drive shaft which goes to the differentials, we actually decided to bolt an electric motor horizontally. And what it does is it powers that differential right on the axle itself. That's why it's called an E-axle.
So you have electric, you have wires, cables that are going from there to your E-axle, and it's powering that. You eliminated the drive shaft and instead put in an electric current.
Exactly, yeah. And we think it's not only a more economical solution, but it actually provides a lot more robust in terms of its performance, right? Because instead of having a drive shaft, which could snap right under the immense load of an electric motor, we just eliminated it. And guess what? With that elimination of the drive line, we now have tons of space to put batteries, right? So it was a no-brainer. I'm so happy that we ended up figuring that out on Carl.
I'm not an electrician, but I do know there's a bit of a difference in AC and DC power. How have you navigated that?
Yeah, so what we ended up doing is really focused on doing high voltage DC, which is direct current, for our battery system. It'll be operating about 600 volts, and that'll be sending electricity from the batteries to the drive motors. The drive motors are actually AC powered. So what an E-axle has underneath it is an inverter. And that inverter has all these little semiconductors and MOSFETs. And it switches rapidly at 60 times a second to convert the DC over to AC power. And we're talking some serious high voltage, 480 volts, three-phase on every single one of those motors. And those motors are fine calibrated to communicate like in split seconds over to the throttle pedal so that you have that consistent power flow. And what's neat too about the generator piece is that's actually doing the reverse, right? So that generator is in AC, produces 480 volt three-phase, and that actually gets bolted onto a rectifier. Rectification is DC going to AC. And in this case, this is actually going into like an opposite of an inverter. It actually smooths out that current from a sinusoidal wave to a flat form DC at about, in this case, 600 volts. And that only goes directly to the batteries, but it can also flow through the batteries to the electric motor. So, you know, it's pretty funny. You have both an inverter as well as a rectifier working together to turn those wheels. It's pretty cool.
Now, the generator is not the only thing that can provide charge to those batteries. Can you tell us a little bit about regenerative braking?
You bet, yeah. I'm so glad you mentioned that because that's the most critical piece of this puzzle. Right now, when you're driving a truck and you're going downhill, you're actually using that fuel to stop you, to hold you back. And what we decided to do with this system is you have those e-axles holding you back, and not only doing it really well, but generating you power. So it's saving you fuel instead of burning fuel to keep you back, right? It's just a cool system. So what it does is those e-axles will be, instead of taking energy, will be acting like a generator. And so just like that generator that we have under the hood, by the way, it will never be on when you need the regen braking, because regen will produce so much energy. We require an additional circuit that comes off of it called a snubber. And that expels energy, the extra energy you get off regen, because it's insane how powerful it is. You actually got to bleed off the excess power through heat to protect the batteries, because you don't want to overcharge the batteries when you're going downhill. That's how powerful it is.
Yeah. So you can potentially produce more power than your batteries will be able to store, and you have to have an overflow for it, and that's your snubber.
Yeah, exactly, yeah. A really important design. That's what we're working so hard on, is systems and they're in place for those redundancies, for when you're at the top of the hill and you're already fully charged. You have to be able to expel that energy, because if not, you'll blow up your batteries. And it's really cool, right? The inverters that actually take that energy typically to turn the wheels actually turn into a rectifier immediately on the fly when you are starting to brake and need that pullback force from the regen. And it's all done through computers and beautiful design.
I imagine all that charge going into the batteries would create heat, and then also, being a logging truck in North America, you'd have to worry about cold, because cold can really kill batteries. What have you done to problem solve those issues?
Yeah, sure can, right? We got some extreme weather on both sides. So the inverters that actually turn the wheels get extremely hot in the summer months, as well as even in the winter months. So we need to have constant cooling going through the system. We chose to do liquid cooling and heating. What that entails is we have this half and half sort of glycol and water mixture. We actually will use the standard issued cooling liquid that you use in a typical rad for a semi-truck, so that people can refill these reservoirs themselves and do the regular maintenance. It's very simple. It's just a reservoir which then gets connected to a rad. That rad will cool while you're in motion, the fluid that's passing through it, and that gets pumped into all these apparatuses like we're talking about, right? So we have the rectifier through the generator, we got the batteries, of course, the inverters. We also have a bunch of ancillary equipment like the air compressor, the power steering module. All these units produce heat, and we're using liquid cooling, kind of like a computer does, to leach all of that heat using Coulomb's law in fluid dynamics.
So I'm kind of hearing that you have coolant lines running through your batteries to not only cool them in the summer, but to keep them warm in the winter?
Yeah, so I didn't really mention the heat yet, and it was really important that we not only figure out how to keep the batteries warm during the wintertime during operation, but also when it's just sitting down, because when your truck is sitting and basically waiting for your next shift in the winter months, you still need to heat your batteries above a certain temperature. Reason being is your batteries are pretty fragile, right? We don't want them to be exposed to minus 30 degrees Celsius. We actually kind of want your batteries to be always at about 10 degrees. So we ended up designing as a system where if you are parking your truck outside in the winter, which a lot of operators will, you'll be using a little bit of fuel, and that will turn a heater on. That heat core will actually continually heat the batteries as a priority to about 10 degrees C. And that makes sure that they're in perfect health. You can always monitor them. You can charge them on the fly if you need to. And it's super critical that you do heat those batteries as a first priority. What's great though is that it's really the only thing you got to worry about heating. Otherwise your cab, right? Most of the electronics can actually take minus 40 degrees, no problem. It's your batteries that really were the ones that you not only have to cool properly, but also heat as well. And I'm so glad that we figured that out.
So a couple of the most important parts of battery life are the cooling, which can kill them, or the cold, which can kill them, and then also the draining the batteries all the way down. Mm-hmm. So you won't be doing either of those. You'll have your generator, which will keep them at above a certain level, I'd imagine. How?
Yeah. Like we obviously have incorporated fast charging from ports, right? There's CCS2 ports, North American standards. We didn't use the Tesla or any other proprietary charging system. We're using the standard one in North America that you can basically pull up to any charger right now and plug it in. But we know that's going to be a rare thing, right? People are going to be working in the bush and then going home at night and parking it. And why build charging infrastructure at your place if you don't need it? You got your generator that's efficiently making electrons that'll go to your battery system. So it was important that we had this generator, which not only can do a very reliable job of charging your batteries on the fly while driving, but also senses when your batteries are getting at that point where it needs that charge. And that's when I have incorporated potentiometers, which are voltage sensors, which actively, like at the split second, will always monitor the voltage of every single one of the cells in the batteries. There's going to be about 172 cells individually, which communicate into a mainframe. And by being able to monitor every single one of those cells, we can monitor the average. And then when it dips below a certain amount, Chase and I will experiment between anywhere from 30, 40, 50, 60, 70% even to see which is the most efficient. And it'll actually turn the generator on automatically. And then it'll charge the battery quite rapidly while you're driving. And then we'll probably go to like 98% or even maybe 100%, somewhere in that band. And it'll shut the generator off, right? So you can continue driving until you get to that low point again. And then it'll automatically turn the generator on. And that cycle will just continue throughout your shift. And voila, that's the secret of the electric semi.
History in the making.
Yeah, we're having a lot of fun. And it's wild to think that all these systems I've designed in the past, those smaller 48 volt systems for solar arrays, which had to automatically turn a generator on anyway. You can't really build an off-grid solar system without a generator. You need that redundancy. So I'm so glad that all those lessons I learned from building those systems, totally applicable to this electric semi. So we've already figured out those things. It's about probably making it into a smaller, more convenient package.